Hello, student. Welcome. In today's lesson, we will learn about the logarithmic functions. Now, as a reminder, this is section 4 in module 5, that is 5.4. You must watch 5.3 before you watch this video. So, if you have not watched 5.3, please go back and watch that video first, because in that video we study logarithm and its properties, which are essential to understand the logarithmic functions. Okay, the organization of this today's lesson is like this. First, we will look at the definition of logarithmic function and the domain and ranges. Then we will go through a sequence of subtopics in which we will explore and try to deepen our understanding of logarithmic functions with various, um, in some sense, independent, but in some way all connected, different independent small topics. Okay. So like graph, some of them are based on graphs and how to graph and what can we learn from the graph of these functions. And then some of them would be about um, finding the domain and ranges when there is a more complicated expression than just x. And then we will be talking about the relation with the exponential function, of course. And after a sequence of subtopics like that, and in each of them we will be it will be based on examples wherever possible. We will work out many examples, and at the end we will do some additional practice problems. Okay, now get ready. Here we begin. Now recall the definition of logarithm. That is, if y is equal to b to the x, then x is log of y with base b, right? So that is the definition of logarithm. But if you think of y and x as variables, that also defines the logarithmic function. Now here x is a function of y as a logarithm, but you can replace, you can interchange them and write y as a function of x. We understand that. That is, a logarithmic function is the inverse of an exponential function. What we just did there shows this, right? If y is exponential function of x, then x is a logarithmic function of y. So logarithmic function is the inverse of an exponential function. We use the fact that the domain of an invertible function, whenever a function has an inverse, the domain of that function is the range of its inverse, and vice versa, right? That's the relation between domain and ranges of a function and its inverse when it exists. So we know, we have studied the exponential function in detail before. So we know the domain of exponential function is negative infinity to infinity. That means the range of the logarithmic function should be negative infinity to infinity. And the range of exponential function, remember, all like, I'm talking about, okay, I should have mentioned this here. B is greater than 0. Okay. So when you take any exponent of b, right, the values are always positive. So the range was 0 to infinity. That means the domain of logarithmic function is 0 to infinity. That is a first important thing to remember about logarithmic function. You cannot define log of either even 0 or negative. Logarithm is defined only for positive numbers. Okay, very important thing to remember. That's about domain and range. Let us try to understand more graphically. Okay, so what are we doing here? Graphing a logarithmic function given the graph of its inverse. What is the inverse? The exponential function. Okay, so you have this exponential function here. My first challenge to you, write its equation. Okay, so what I mean is, you know this is y equals b to the x. What is the b? I want you to figure that out. Give a thought, second of thought. Whenever I ask a question like this, pause and think and then continue. Okay, and I should not wait too much in the video, Okay, I hope you have figured out. At 1, the value is 4, right? So that means this b here is 4. It's y equals 4 to the x. And it is increasing from left to right. So you knew that b is greater than 1. But the fact that um, a point on the graph is 1 comma 4 tells you it is particularly 4 to the x. Okay, now that's the graph, which means, okay, so let me write that here. Y equals 4 to the x. The graph of y equals 4 to the x is what we have on the right. On the left, we would like to draw the graph of what is the inverse. Okay, 2 steps. Okay, first, from here, if you apply the log on both sides, log base 4 of y equals x, right? Or x equals log of y to the base 4. But I'm going to interchange the x and y to write the function in terms of y here. So the function we are going to graph is y equals log to the base 4 of x. That would be the inverse function, right? Okay. And how will we graph that? Using the graphs. Okay. Let us begin. So you have a point 0, 1 here. That means you should have a point. Okay. Here is my x-axis and here's my y-axis. And here is the origin. Those are the axes. So a corresponding point on this graph should be 1, 0, right? Inverse functions, x and y interchange. We marked another point 1, 4 earlier. So in this graph, I must have 1, 2, 3, 4, 1 here. 4, 1. Okay. 0, 0 is not in the graph. I was just trying to say that's the origin. Okay, so we have 2 points in the graph that we need. How can I get some more points? We got points that are on the right side. Now let's try to get some points on the left. Okay. So if I look at this point here, its coordinate would be -1.25. That's 1/4. Okay. So which means on my graph on the left, there should be 0.4 is 25 somewhere there. So at that point, the value is -1. So the point should be somewhere here. Okay. Or just for simplicity, let me move it a little bit to the right so I can sketch one more point. And if you go to -2, okay, the value is 1/16. I'm not sure what it is in decimal, so I'm just writing 1/16. Okay, 0.125, 0.0625. That means on the graph, when you are at 0.0625, now I'm going to zoom out and show you, okay, because it's really hard to see. We are here, half of, 1 over, not even half, 1/4 of 1/4. Okay. So we are somewhere there, and there the value is -2. We are somewhere there, not touching the axis yet. Okay, but close to it. That's really difficult to show it. Something like that. Okay, now you see the pattern, what's happening. I'm going to draw the freehand diagram. And it's going to, okay, that doesn't look asymptotic like that. That, my friend, is the graph of log x. Okay, in this case, the base is 4. Okay, now just like we exponential function had some specific characteristics, if you remember, we discussed in that video, the logarithmic function also have some characteristics. I will just talk about them orally and write some notes on the uh, available space. You do the same. Okay. Number one, the x-intercept. Okay. The x-intercept will always be 1, 0. And that is also the way you can remember that specific very important property of logarithm, right? Log of 1 is always 0. So for any log x, not just log x and to the base 4, log x to any base will have the x-intercept 1, 0. Just like every exponential function has the y-intercept 0, 1. Okay. First thing. Second thing, when the base of that logarithm is greater than 1, like in this case 4, uh, log of this will go to negative infinity as x goes to 0. Okay, so when the base is greater than 1, log x will go to negative infinity, that you can see here, falling to negative infinity down when you get closer to 0. And what about on the right side? Okay, log x of the will go to infinity as x goes to infinity, again when b is greater than 1. Okay, when the base is greater than 1. On the right side it goes to infinity, on the towards 0 it goes to negative infinity. That is why, remember, the range is negative infinity to infinity, we had said earlier. It looks like the graph is growing ever more slowly, but it will not become horizontal. It is not going to become asymptotic to a horizontal line. It is going to go very slowly, but eventually it will go to infinity. Okay. Just like exponential growth is fast, rapid, logarithmic growth is the inverse, right? The opposite. Logarithmic growth is very, very slow. So that is another common wisdom, in language. So I'm going to write that here. Okay. And you might well remember it. Logarithmic growth is quote unquote slow. Okay. And you can see that in this graph. As you go to the right, it will grow more and more slowly. It almost looks like a horizontal line, although eventually it goes to infinity. Okay, at a what you call the tortoise's pace. Okay, very slowly. Okay, so one last look. Have a look at the exponential function on the right, logarithmic function at the left. Let all the concepts sink in. We will go to more concepts. Now we graphed the logarithmic function just now as the inverse of exponential function, and we didn't do any other analysis. I just graphed it as an inverse. Now let us graph it independently. That is just from the equation of the log. Okay. So let's say you want to graph y equals log of x with base 2. So what we will do is first we will compute a table of values on the left and then plot them in the graph. In order to do that, we will remember that log is defined only for positive values. So this does not exist. That does not exist. You cannot define log x for -1 and 0. And then another important property, log of 1 is 0, right? And then log of 2, but the base is 2, right? Log of 2 with base 2. Now you remember from the previous video which I was talking about, that's equal to 1. Okay, log of 2 with base 2 is 1. And then similarly when it is 4, that will be 2 because that's 2 squared. And now log of 1 over 2 is negative log 2, right? I'm also writing some properties here as a review, as a reminder, okay? So when you evaluate log 1 over 2, one of the properties is this becomes log 1 minus log 2 by using the quotient rule. Log 1 is 0, so it's basically negative log 2. Whatever base, okay? So in this case, the base is 2. So which means this is -1. And similarly, that's -2. Okay? Now, you should be comfortable evaluating those, okay? That's what I meant to say there. Okay, let's plot them now. Remember, 1, 0 is always the intercept. So at 1, it is 0. At 2, it is 1. At 4, the output is 2. And at 1 over 2, which is half here, the output is -1. At 1 over 4, which is here, the output is -2, and so on. So you see the graph like before, like the log 4 of x, but you can see that it will look like it's increasing for a while because the base is only 2, but eventually it will start becoming slower. Okay, and that is the graph of y equals log x base 2. All right, here is an opportunity for you to practice, but the base is half now. Remember that. Okay, so again, whatever the base, as long as the base is positive, otherwise you cannot define. As long as the base is positive, so the log is defined, it's a proper function. You cannot define it for negative and 0. And log of 1 will always be 0. Okay, now what's going to be log of 2? That's the interesting one, right? uh, so I'm talking about evaluating log of 2 when the base is half. Okay, different ways you can approach this. One is you can use the property that we just used a while ago, that if you do the reciprocal of the argument for the log, that it becomes negative, right? So this is negative log to the base half of half. Reciprocal of 2 is 1 over 2. Now log of half to the base half is 1, so this is -1. Okay, so you can use that technique to evaluate. So at 2, this is -1 because the base is half here. Okay, remember it. Okay. right? Um, what's another way of evaluating? Okay, that's the best way actually. Um, Similarly, log of 4. Okay, now I'll write here and then I'm going to erase it. Log of 4 with base half. I would write this as um, log of base half, and 4 is 1 over 4 to the power negative 1, and then you can write it as log half 1 over 2 to the power negative 2, right? Then bring the negative to the coefficient, so you see, and then rest is 1. Similarly, log of half with the base half is of course 1, and 1/4 is half squared, so it will be 2. Okay, all right. Now let us see what kind of graph we are going to get. At 1, it is the output is 0, y value is 0, that's always the case. But when you go to 2, the value is negative 1 now. And at 4, the value is negative 2. Okay, so it's decreasing towards the right. What happens on the left? At half, the value is 1. At 1/4, half of half, the value is 2. So now the pattern is clear. Your graph is going to be this. Okay, and now I'm going to make some observations. This is the graph of y equals log base b of x, where b is less than 1. Okay, and I'll just draw a very rough graph now, what we did previously, which was this. And that would be the graph of y equals log x with base b when b is greater than 1. Okay, so I want you to like study this or understand this and connect this with the similar situation with exponential functions, right? When the base is greater than 1, from left to right, it increases and goes through the point 0, 1. When the base is less than 1, it was exponential decay, right? Decreasing from left to right, and they meet at the point 0, 1 on y-axis. Here, these are inverse functions. Everything is opposite, right? Just the same way, but similar behavior between when the base is greater than 1, base is less than 1. They meet at the point 1, 0, which is the common x-intercept. Okay, all right. So we have been exploring, as I was saying, the layout of this lesson is we have been exploring these different ideas with small subtopics. Next, so in the process, we are understanding the logarithmic functions more and more, different aspects of them. So what are we doing now? We are trying to look at the impact of that log function when you compose it with other functions, in terms of the domain, right? What is the effect of applying a log to some other function? What does it do to the domain? What values get restricted or not restricted? We'll see. Okay. So the first example here, y equals ln x to the 4 plus 8. Now I want you to remember the concept of composition of functions. Okay. To make sure that you have remembered it, I will give you this challenge. Express that y as a function of f of g of x. Remember the inner and outer. So I want you to identify what is the inner function and what is the outer function there. Okay. So you should know, like you should be able to write what is g of x and what is f of x. Inner is g of x, outer is f of x, right? Okay. And check your answer. As you can see, the inner is x to the 4 plus 8, right? And outer is ln x. That's where the logarithmic function is here. Okay. And when you compose them, you get ln x to the 4 plus 8. Now, what is the impact of the natural log function here? The impact is like this. Okay, I'm going to write now. For y to be defined. When we write this, we always mean for y to exist as a real number. Okay, for y to have a real value. That's what we mean when you say for y to be defined. For y to be defined, that argument for the log, which is x to the 4 plus 8, right? That x to the 4 plus 8 is the input to the natural log function. That must be greater than 0. That is the main feature of log function in terms of domain, right? The domain of log is only positive numbers. So in this case, I won't say x should be greater than 0. I will say what is being fed to the log machine, that should be greater than 0. So x to the 4 plus 8 should be greater than 0. The rest is to solve the inequality. Now take the 8 to the other side. You get x to the 4 greater than negative 8. Now I'm thinking x to the 4 is like even power. That's always non-negative. It is always going to be greater than any negative number, right? So which is true for all x. That means all real x. Okay, which is true for all x, meaning for all real number x. Hence, your conclusion now would be the domain of this function. Okay, that function ln x to the 4 plus 8 is everything. There is no restriction. Okay. Now don't say that, oh, this was a logarithmic function. We say the domain should be only positive numbers. And how am I saying domain is all real numbers here again? We're talking about composition function. Okay. You can give any number, real number. Let's say you take a negative number. You would be raising it to the power 4, so it becomes positive, and then you add 8 to it, more positive. Then you feed into the natural log function and you will be all right. Okay. Now repeat the exercise for the next problem and then watch me. Same argument. Okay. Let me just write it in a different language now. Y exists as a real number for x such that negative x square plus 16 is greater than 0, right? Because that is the input to the natural log function. Now I have to solve that inequality. That implies negative x square is greater than negative 16. Both sides negative, so you multiply by negative 1. And remember to change the direction of the inequality, right? X square is less than 16. And That means negative root 16, which is negative 4, will be less than x, which will be less than 4. Right? Whenever x square is less than a positive number, that is the conclusion. We have talked about that in the earlier chapters. Okay. All right. Uh, you can just circle it because that's a domain anyways. We have already figured out. No, you can write that as your domain, or if you want to write in a different way, you can say, or you can say negative 4 to 4 as an interval. Okay. Next, we will compare the graphs of the exponential function and its exact inverse, the logarithmic function. I mean, like with the same base. Okay, so they're the not inverse in idea, the actually inverse functions. We want to look at their graphs in the same grid. Okay, so there are some things to observe there. Now, here are the graphs of e to the x and ln x. Very simple challenge first. Identify which is ln x and which is e to the x. Okay, I hope it was not difficult. Right? Now, these are the graphs of two inverse functions, and what are the things I observe? And some of the things I say now, you might find that we have talked about these ideas before also. Okay, so it's not something new. If you draw a line like that in the middle, whose equation is y equals x, right? And you see that these two are mirror images, like reflection on that line. And that's what inverse functions do graphically. Okay, so I'll just make that fact as a simple observation here. As must be, I'll say, as must be, the graphs are reflections of each other on y equals x. Okay, what other note? This will be some repetitions. Okay, I've said these things before also. E to the x grows rapidly as x increases. For large x, it's rapid growth. You may not see the rapid growth if you look at the negative side. Okay, it's growing slowly, for a long, long time. After 1x, after 0 actually, after x equals 0, if you look at the y-axis, beyond that, it starts to grow rapidly. And what is the counterpart doing? Ln x grows slowly. I want to make it a comparative thing here. Okay, so I'm writing grows slower as x increases. Okay, ln x grows more slowly, e to the x grows more rapidly. And you can write any number of notes. These are, again, if they are repetition, that's because they are important concepts. Okay. All right. I'm doing all this again and again, so some things will get imprinted in your understanding about logarithmic functions and exponential functions. All right. Let us move on. As we always do, let's do some transformations on these functions. Some shifts. Okay. What's the difference between ln x plus 2 and ln of x plus 2? Okay. So in theory, we know this already. This is adding to the output value, right? So that is a vertical shift 2 units. And this is modifying the input, right? Ln of x plus 2. You change the input itself. And that creates a horizontal shift. Left in this case. Okay? Because it's plus 2. Okay. So with just that idea, let us sketch the graph. So ln x plus 2 will be vertically 2 units. So say instead of at 1, instead of 0, it will be there. At 2, it will be here. At 4, it is here. At 3, it will be here, and so on. Okay. And there, and so on. The intercept, so the asymptote is still the y-axis, but shifted up by 2 units. So that is ln x plus 2. Go ahead and sketch ln x plus 2. And that would be shifting 2 units left. So 1, 0 will be negative 1, 0. 2, some value there would be here. 3 would be here. 4 will be slightly up, and so on. And it will then decrease here. Everything 2 units to the right, and so on. Okay. And important thing is you can sketch the graph of the asymptote. Okay. So y equals, sorry, not y, x equals negative 2 would be your new asymptote. Like that. Okay. So the rate function here is y equals ln plus 2. Okay. Next, we are looking at something which is used in calculations and computations. Okay. So we have used the properties of logarithm to evaluate in the previous section. In this section, we have studied both of these earlier. Okay. In this exercise, we are trying to put them together, and so that we can remember. If I have to evaluate the log value for any quantity, there are these 3 different techniques I can follow. Okay, we will see them in A, B, and C. One is you can evaluate it analytically by using the definition. Okay, how does that work? Let's see. So you say let x equals log to the base 4 of 1/8, right? That means by definition 4 to the x, right? Remember log, if you bring it to the other side, becomes the exponent with the same base. So 4 to the x equals 1/8. Now it's an equation I got to solve. Okay. And that immediately reminds me that in solving exponential equations, I can try to make the bases equal. 4 and 8. That reminds something. Both are powers of 2. So you can write 2 to the 2x. And 1 over 8 is 1 over 2 cubed, which you can then write as 2 to the negative 3. Okay. Now you have two sides equal and their bases are same 2. Okay. So continuing here, that implies 2x should be equal to that negative 3 by equating the bases. Divide both sides by 2 and you get x equals negative 3 over 2. Okay. So this is the way, and that's what we are trying to evaluate. Okay, by the way, if you thought that we solved the equation, x was that quantity which we wanted to evaluate, right? So we evaluated this indirectly by solving an equation by using the definition of logarithm to convert that from logarithm to exponential and solve it. Okay. Maybe I should also mention that in the title itself, the method we are following here is evaluating analytically using the definition, I would say, to convert, okay, in exponential form. So you use the definition to convert to exponential form and then solve that equation and you have the value of x to convert to exponential. Okay, that's one method. What's the other method? Evaluate directly by using the change of base formula. Okay, this you should be able to remember. We have done this before. What does the change of base formula say? You can write this as log with any base of 1 over 8 divided by log of 4. Okay, with any base. So I'm going to write base 2. Obviously, because it's easy to express, 1 over 8 and 4 in terms of 2, right? Same idea that we used in the solving the exponential earlier. Okay, these are just different ways of writing. Fundamentals are the same. Now, continuing here, that will be equal to, now 1 over 8 again is 2 to the negative 3, So log base 2 of 2 to the negative 3 log base 2 of 2 squared. So negative 3 to the front in the numerator, 2 to the front in the denominator. And log 2 of 2 is 1, so negative 3 over 2. Okay. And yet one more method would be to just look at the graph. Now for that, you will be watching, you will be doing this on either on a graphing calculator or on an online graphing tool. And then once you have the graph, in the graph you go to the point, like, so which point, and that's what I want you to discuss. Okay, suppose I'm just drawing a graph here which you would have on your calculator or on your screen, and in that you are looking, so the graph of log 4 is this, right? I didn't write that, we have already mentioned that here. And what is the point I should be looking at? 1/8, right? So on the graph, you should go to where x is 1/8, and now that's going to be challenging. Okay, so you have to zoom in, zoom in, zoom in until you reach 1/8 on x value, and then go to the graph corresponding point at 1/8. You know, it seems the value would be at -3 over. You will figure that in the graph, okay, at -1.5, and hence you will know that that's the -3 over 2 is there. Okay, all right. And in calculator graph, there is a way where you can choose the x value and it will show you, what the corresponding y value will be. In an online graph, typically you can move your mouse, or the cursor and point to different points in the graph and it will show you the coordinates. Okay. So you move that until your x coordinate is 1/8 and then look for the y coordinate and that's your answer. That is the method of evaluating by looking at the graph. Okay. Importantly, again, I will say, if you have to evaluate log of 1/8 with base 4, you would look at the graph of log x with base 4. You have to choose the correct graph. That is important. Then choose the graph with the same base, basically. And then go to the x value, wherever you are evaluating. Okay. Another problem. Evaluate that using now, this is like for you to practice. Okay. We have done 3 different methods just now. You go ahead and do this by all 3 methods and get the same answer. Okay, check with me now. So first method, I could do them in any order. Okay, I don't remember the order. I'll just go through all 3 methods. Okay, I remember actually. The first was definition method. So let x equals log 1/5 of 25, and that means 1/5 to the power x should be 25, but then 1/5 is 5 to the -1, so that's 5 to the negative x equals 5 squared. Not difficult to see, x will be -2. Okay, I skip the step when you compare the exponents. And the second method was change of base formula that we applied. So log of 1/5, sorry, log of 25 base 1/5, that will be log 25, any base, right? So I'm going to choose base 5, and log 1/5 in the denominator, same base 5. Okay, then you see that that's log base 5 of 5 squared, that is log base 5 of 5 to the -1. So 2 divided by -1, they come to the coefficient, which is -2, as we had seen in first method. And the method 3, you look at the graph, right? I was saying choose an appropriate graph. The graph you should be choosing should be the graph of y equals log 1/5 x. Okay. Now that reminds me, the graph of log 1/5 x is going to look like this, right? And apparently now you have to zoom out now. Okay, zoom out sufficiently. So let's say this is at 25, and you'll see that the corresponding point on the graph at 25 would be -2. That is how you know the answer is -2. Okay, all right. finding the equation of the inverse of a general exponential function. So what are we doing here? We have been, you know, saying this many times. The logarithmic functions are the inverses of exponential functions. But whenever we did that, we applied it to the simplest function like b to the x, and we got its inverse. Okay. Now suppose you have a general exponential function which might be some kind of shifts. When I say general here, what you need to understand is the exponential function has been composed with some polynomials. Okay, it has been either been stretched or reflected or shifted, has been generalized, the exponential function. Now find the corresponding logarithmic function. you know Now that logarithmic function also is not going to be just log of some base x, right? There would be some things added, subtracted, multiplied. We need to get that. And this again is a method we have already learned, how to find the inverse of any function. We have learned that technique earlier, right? Finding the inverse of a function. Three-step process. So you say let y equals given function. Okay. And what was the second step? Solve this equation for x. This is y in terms of x. You want to get x in terms of y. So you will say y plus 5 equals half to the power x. And now if I want to bring the x down, of course, you apply the log now. But what is the base? Base is half. So log base half of y plus 5 will be equal to x by definition. Okay. That is, I'm writing x in terms of y. So I would write x on the left side, log base half of y plus 5. And finally, interchange x and y. That step is after here. Okay. And that gives you y equals log half of x plus y. That would be the inverse function. Okay. So you see the inverse is a logarithmic function which has also been transformed. So if you take a general exponential function, its inverse is going to be a general logarithmic function. Okay. This is for your practice. Do it and check with me. As always, let y equals 4 times 3 to the x. That dot is times, okay, plus 1. So we are trying to solve for x. Let me write that on the left equals y. 4 times 3 to the x, subtract 1 on the right side, divide by 4 both sides. So 3 to the x will be y minus 1 divided by 4. Okay, both sides divided by 4, it gives you that. And we need x, right? Base is 3. So you apply the log with base 3. Exponential on the other side becomes logarithm. That is how I remember it. Okay, so basically you are applying log base 3 on both sides. On the left side you are left with x, on the right side that expression. and then you interchange. So this step we go here. That gives you y equals log to the base 3 of x minus 1 over 4. Okay, and that's it. That's the answer. But I'm reminded of mentioning something here. It not necessary, but it is a good idea, and you would be showing your skill if you also mention any restriction on x. Because in as an exponential function, there was no problem, right? Because the domain of exponential function is all real numbers. But now the inverse is logarithmic function. So the domain may not be all real numbers. What is the restricted domain? Not very difficult to figure out. You can easily note that. Okay, if it is x plus 5 here, then you know that argument x plus 5 has to be positive, right? So you can actually put a comma and mention that as your part of your answer. Okay, y equals log of x plus 5 base half, and then you say x greater than negative 5. Why? Because x plus 5 has to be greater than 0. No? And you solve, you get x greater than negative 5. In the same way here, can you tell me what should the restriction on x? Comma, you would say x greater than 1. Divided by 4 does not matter. Okay, it doesn't change the positive to negative, it stays positive. Your x minus 1 should be greater than 0. So x should be greater than 1. Okay, all right. So we have studied everything about logarithmic functions. Now we are doing some practice problems to solidify our understanding. Okay, additional practice problems. We have done already enough many examples. These are additional problems. Solve negative 4 to the x plus 9 equal to 0 for x, expressing x in terms of a base 4 logarithm. Please do it yourself and check with me. That is our given equation. I want to solve for x, so I'm going to take the constant number to the right side. Both sides are negative, so I can multiply by negative 1. It's equality anyway, so I don't have to worry about changing the direction, right? Now I have 4 to the x. Base of that exponential function is 4. So you apply the log with base 4. That's what we needed, right? As a base 4 logarithm. Expressing x in terms of a base 4 logarithm, which we have done here. So we are done. Okay. All right. Prove the identity. It's a very interesting identity. Natural log ln absolute value, the quantity, plus ln absolute value, that quantity, equals 2 ln a. Okay. So you should have started like this, right? You start with one of the sides whenever you have to prove the identity. You start LHS here means left hand side. So you start with one of the sides and get it to become the other side. So on the left side, I have that expression ln something plus ln something. In my mind, that immediately triggers the property. What is the property? The product rule. Okay, if you are adding ln A plus ln B, you can as well multiply them. So x plus under root x square plus a square and x minus under root x square plus a square can be multiplied, and you put that in a parenthesis. Put that in absolute bar. Okay. Now how does that help me? I am looking at what am I multiplying. X plus a quantity and x minus the same quantity, like a plus b times a minus b. Okay. And that's going to be a squared minus b squared. I will write up here in case you need a reminder for that formula. A plus b times a minus b equals a squared minus b squared. Okay. So this would be ln x squared minus under root x squared plus a squared, that is your b squared. A squared minus b squared. That. Okay. Equals ln x squared minus, now under root and square cancels. What do I get? I have to use parentheses. This is super important because I'm subtracting negative, that after cancelling that we are left with x square plus a square. That expression is being subtracted. Okay, now you open the parenthesis. So when you distribute the negative sign, both become negative. And now you cancel the x square minus x square. So ln of absolute value of negative a square. Now we use the absolute value, right? A square is positive, so the absolute value will basically get rid of the negative sign. That is the definition of absolute, right? Then 2 can now go to the front, so we get 2 ln a, which is the right hand side. That is needed to be proved. Okay. All right. In this identity, okay, it was not mentioned, but we we'll take it as a given, okay, that a must be greater than 0. Otherwise, we cannot write it without the absolute value. Okay. Use properties of logarithms to write that expression as a single logarithm with coefficient 1. Okay. That's all the exercise is. Just you have to merge them, you have to combine all of them into a single logarithm. But keep the coefficient of the logarithm 1, which means everything should be ln and in parentheses, everything in. Okay. So you can do in any order, really doesn't matter. Let's say I combine these two first. That would be ln 3 over x, right? The quotient rule. Minus. We want to have the coefficient 1. So this coefficient 5 here, I made 1 to take it inside the natural log in the argument. Okay. So that would be the power rule, right? 2 to the 5. For clarity, let me put parenthesis. So there is no ambiguity. Similarly, this half is a coefficient here. You convert it to the exponent inside. so that the coefficient is 1, y to the half. Okay, what is now ln minus ln plus ln, everything else has been taken care of. So you will do the usual stuff. Ln a minus ln b would be ln a divided by b, and plus would be multiplication times y to the power half. So where there is negative coefficient, that is divided, that divides. When there is a plus, you multiply. Product rule and quotient rule. Okay, all that is left now is to simplify this expression. Okay, and x and 2 to the 5 both are denominators here, they go together. 3 and y to the half are both numerators, they go together. So that will be ln 3 y to the half, I'm going to write as root y. Okay, that looks easier for me. Divided by 2 to the power 5 is 32 times x. That's easier. Good, right? This looks better. Okay, a single neat expression. Okay, we have one last problem to finish it, and that's a word problem. Okay. When sunlight passes through lake water, its initial intensity decreases to a weaker intensity at a depth of x feet according to the formula. Okay. How the intensity decreases is given by this logarithmic function. Ln I minus ln I naught, that is the I naught is the initial intensity, okay, equals negative kx, where k is a positive constant. Solve this equation for I. So which means, that means you need to express I equal to something. I in terms of every other quantity in that equation. Okay, solving for I. Okay, let's begin. I will say given ln I minus ln I naught equals negative kx. Now I want to isolate I, but for that, if I directly take the ln I naught to the right side, it works, okay? But I think that will be lengthy later on. I'm thinking like that because I'm able to think a little ahead and realize that I could first combine these two logarithms, ln I minus ln I naught. You know what happens? That, okay? So now I have only one natural log in the whole equation, which can be converted to exponential easily, right? Now the natural log, if you find it inverse, which I say taking to the other side. When I say taking to the other side, I mean writing its inverse. Okay, becomes the exponential function, right? Natural log, what is the base? Remember, log e is equivalent to written as ln. What I'm writing in the right side here is for you to remember. Okay, ln is natural log, which is log with base e. So that means I divided by I naught will be equal to e to the negative kx. Okay. And so if I have to isolate I, divided by I naught on the right side becomes multiplied by I naught. That's it. Right? I in terms of other quantities. So that is solving for I. Okay. And you can see that there is an exponential function here with a negative uh, term in the exponent because k is positive as it is given there. So for large values of x, that quantity is going to decrease. So the intensity, the resulting intensity I will go on decreasing. You'll get that exponential decay. Graph would be like that, decay. Okay, that brings me to the end of this uh, module. Thank you. I'll see you later.